Okay, can people see that? Yeah, okay. So first of all, thanks very, very much for the invitation. I visited Iran for, well, the only time in my life, about 5.5 years ago, I think. I went to Isfahan, and I still have extremely fond memories of that visit. And so it's nice to be back, if only in a virtual sense. So the talk I'm going to give today is prompted by a question that Manuel Saurin asked me just a few years ago about whether the property of a ring being right coherent was derived invariant. So I'll say a little bit about definitions and so on in a second. When he asked me, I had no idea, but then I remembered an example that I gave in my PhD thesis, which even then was more than 30 years previously, that I realized could be used to give a counterexample. So in this talk, I'll give some examples for other related questions as well. I suspect that some of these things, some of the questions I'm going to address have been answered many times before, but I've not been able to find any references. So I would be very grateful if anyone could sort of point out to me where people have answered these questions, if indeed they have, as I suspect. Okay, so let's start with some basic notation conventions. So I'm going to be talking about rings, fairly general rings. So they'll be associative, not necessarily commutative. If R is a ring, I tend to prefer right modules. So mod R will be the category of right. R modules. And so let me start by going an extra 30 years or so back in time to the idea of Morita equivalence. And so I'm sure everyone is familiar with this, what it means for two rings to be Morita equivalent is simply that their module categories are equivalent categories. So mod R is equivalent to mod S. And the simplest, the most well-known example of this is if we take any ring R, then it's always Morita equivalent to, let's say, 2x2 matrices or generally n by n matrices. And the equivalence between the module categories is easy to describe. Okay, if we take an R module M, then we can take that to the row vectors with 2 entries from M, which is a right module for the 2x2 matrix ring. And if we have a module for the matrix ring, we can just send that to N multiplied by the matrix unit E11. So E11 is just this matrix. Okay, and it's easy to see that these are inverse up to isomorphism. So a question that's often asked is, if we have some property of a ring is it Morita invariant? In other words, a property variant rings is called Morita invariant. If whenever we have two rings that are Morita equivalent, they share this property, or they share having or not having this property. So if, in other words, if it only depends on the module category. Simple examples are, well, the example I gave, the 2x2 matrix ring, shows that one property that's definitely not Morita invariant is commutativity. If we take any commutative ring, for example, the integers, then this is Morita equivalent to the 2x2 matrix ring over Z, and Z is commutative, but the 2x2 matrix ring is not commutative. So commutativity can't be Morita invariant. So this is not a Morita invariant. So some examples that are, well, how do we show that a property is Morita invariant? Well, sometimes it can be fairly complicated, but the most satisfying, I think, way is to find some way of extracting the property directly from the module category. So examples that are Morita invariant well, one example is the center of the ring is Morita invariant, and it is possible to extract this directly from the module category because this is naturally isomorphic to the center of the module category. The center of the ring is the same as the center of the module category, which means just the ring of endomorphisms of the identity functor on the module category. So in other words, the ring of natural transformations from the identity functor to itself. Okay, so this is an example of extracting a Morita invariant property directly from the module category. Another property is the property of being Noetherian. So because I'm dealing with right modules and not necessarily commutative rings, let's talk about the property of being right Noetherian. What's the noun Noetherianity? Something like that. Okay, and so of course this means that every submodule of a finitely generated module is finitely generated, and from the module category we can characterize which modules are finitely generated. That's not so hard to do, and so this property depends only on the module category, not on the ring. So it's kind of handy here to say things in terms of submodules of finitely generated modules rather than talking about ideals of the ring, which gives the ring itself a rather special place in this. But if we talk about general modules and write the definition of being right-Noetherian in terms of those, we can easily see that this depends only on the module category. Another property that is Morita invariant is we could, rather than looking at being right-Noetherian, we could look at two-sided Noetherian rings, in other words, rings that are Noetherian on the right and on the left. This is a little bit more tricky to extract directly from the module category, because along the way we need a lemma, which is that if two rings are Morita equivalent, then their opposite rings are Morita equivalent to one another. Okay, but still, this is a Morita invariant. Another example is right coherence. Okay, so what does this mean? A ring is right coherent. It just means that every finitely generated submodule of a finitely presented module is finitely presented. And just as finitely generated modules can be characterized inside the module category, so can finitely presented modules. And so this is a Morita invariant. So another way of saying that a ring is right coherent is that every kernel of a map between finitely presented modules is finitely presented, which means that the category of finitely presented modules is an abelian subcategory. Of the module category. Okay, so probably many people are a lot more familiar with Noetherian rings than coherent rings. So being Noetherian implies being coherent. But here are some examples of rings that are right coherent, but not right Noetherian. So if we take the polynomial algebra in infinitely many variables, that's not Noetherian, but it is coherent. Of course, this is commutative, so right and left doesn't make any difference for this. If we take a product of, let's say, countably many copies of a field, then that's coherent but not Noetherian. If we take the ring of all algebraic integers, it's another commutative coherent ring that's not Noetherian. And a non-commutative example, if we take the endomorphism ring of an infinite dimensional vector space, then that's coherent but not Noetherian. Okay, so just examples. Okay, so that's all very classical. So now let's talk about derived invariance. So then just to set up my notation, so I prefer looking at co-chain complexes of modules. So So I'll tend to just for keep things uncluttered, I'll tend to leave off subscripts and superscripts when it is obvious what I mean. And so a cochain complex, the terms of the complex are numbered so that the differentials increase degree. So they go from n-1 to mn and so on. Okay, so the definition of the derived category, I'm sure everyone knows, but the objects are the cochain complexes of R modules, and take the category of cochain complexes and invert all the quasi-isomorphisms. In other words, if any cochain map induces an isomorphism on all homology groups or all cohomology groups, then we adjoin an inverse to that. And then this gives the derived category. Okay, so the objects of the derived category are still the cochain complexes. And as usual, I'll think of the module category as a subcategory of the derived category just by identifying a module M with the cochain complex, which has M in degree 0 and 0 everywhere else. This identifies the module category with a full subcategory of the derived category. And we'll say that generalizing the idea of Morita invariance, so two rings are called derived invariant, derive equivalent, sorry. If their derived categories are equivalent. So to be precise here, I should say derived equivalent with an equivalence preserving some extra structure. So derived the equivalent as triangulated categories. Okay, and just as a Morita invariant is something that's preserved under Morita equivalence, a property or invariant of a ring is a derived invariant. Is an invariant or property that depends only on the derived category. So every Morita invariant is obviously a derived invariant because the derived category depends only on the module category. So, sorry, yeah. Sorry, confusing myself. No, ignore that. Ignore that. Sorry. sorry, what I meant to say was every derived invariant is a Morita invariant, okay? Because if two rings have the same module category, they certainly have the same derived category. So some examples of things that are derived invariant. Well, the center of a ring turns out to be derived invariant. It depends only on the derived category. So it is not quite so easy to prove as for the case of the fact that it's a Morita invariant. And I'm not sure I know any proof of this that you could really sensibly think of as extracting the center of the ring directly from the derived category. And then there are all sorts of other examples, so various homological invariants. So the Hochschild cohomology, at least if the ring is an algebra over a field, the algebraic K-theory. There are all sorts of sophisticated things like this. Okay, but what about less sophisticated ideas? What about things like being right Noetherian, right coherent, so on? Okay, and so as I said at the beginning, so Manuel Sarin asked me just a small number of years ago whether I knew whether the property of being right coherent was a derived invariant. So it's definitely a Morita invariant. Is it a derived invariant? And the reason he had for wanting to know this was that if the answer was yes, if it was a derived invariant, then that would have simplified considerably the hypotheses in a theorem of himself and some of his co-authors. So he had two rings. He had to assume they were both coherent. And he wanted to know whether just knowing one of them was coherent would be enough. Okay, so when he asked me this, I said, I have no idea. But then I remembered a construction that appeared in my thesis. I don't think it ever actually appeared in print, but in a published form. But this is a construction that is really quite old. It's been used many, many times to give counterexamples of properties of rings. And this is the idea of taking triangular matrix rings. So let's do this in the following level of generality. Suppose we have some ring homomorphism, ring A to a ring B. So this means that if we have any B module, we can regard it as an A module just by restricting along this homomorphism phi. And in particular, B itself will be a bimodule for A. So let's let R be the following triangular matrix ring. So the 2x2 matrices with entries from A, from B, bottom left entry is 0, bottom right entry is from B. So the fact that we can multiply elements of A by elements of B by using the homomorphism phi means that this is a well-defined ring. So what do right modules for this ring look like? Well, if X is an R module, the right R module, then multiplying by x on the right by the matrix unit E11, this is an A module, because A is just E11 times R times E11. X times E22 is a B module. And we have a homomorphism given by the top matrices spotted in the top right. So if we take little m to m times the matrix unit E12, this maps x times E1 to x times E22. And this is an A module homomorphism from x E11 to x E22. And this structure determines the module, the original module X. So in other words, an R module is, or it is determined by exactly the same data. An A module homomorphism from a right A module to a right B module. Okay, and we can do something similar, but putting the zero entry in the top right instead of the bottom left. Okay, so similarly, if we take S to be this triangular matrix ring, then an S module, a right S module, is just an A module homomorphism but this time from a B module to an A module. So the data of an S module is just the data of choosing a B module and an A module and a homomorphism from the B module to the A module. Let me just point out that if the rings A and B are commutative, then all we're doing is taking the transpose to get from R to S. So if A and B are commutative, then S is just the opposite ring to R. Okay, if not, if the rings A and B are non-commutative, then to get the opposite ring of R, we'd have to change the definition of S, put the opposite rings of A and B on the diagonal rather than just A and B themselves. Okay, so I claim that these two rings R and S are derived equivalent. So fairly straightforward to prove this using theory of Morita theory for derived categories. You can easily write down a tilting complex for R and calculate that its endomorphism ring is S. But it's actually possible to describe the equivalence of derived categories much more directly in this case. So let me go to. Okay, so let's think about an object in the derived category of R. So this just looks like a commutative diagram of the following kind, okay, because what is an R module? An R module is just an A module homomorphism from an A module to a B module. So each column of this diagram represents an R module. The M's are A modules, the N's are B modules. So you can think of it either as a complex of R modules, or you can think of it as a complex of A modules and a complex of B modules and a chain map of A modules between them. Okay, so that's what an object in the derived category of R looks like. Okay, so now what we can do is thinking of this just as two complexes of A modules. Okay, so every B module is an A module by restriction. We can take this and construct its mapping cone. Okay, so we just take the mapping cone, the usual construction. Then what we get as the mapping cone is a complex of A modules. Okay, because every B module is an A module. And so what we have in each column is a homomorphism of A modules from a B module to an A module. In other words, these columns here are just S modules. And so what we get here is an object of the derived category of S. So the f of x, this is x, which is in the derived category of R. Then f of x will be in the derived category of S. And there's a dual construction, which is easy to check, is inverse to this up to quasi-isomorphism. So this construction gives an equivalence of categories from the derived category of R to the derived category of S. Okay, so let me just go to the other document. So what we can do now is use this to give lots of examples of derived equivalent rings. And this allows us to recycle lots of well-known examples. Okay, so here is an easy way then of seeing that being right Noetherian is not a derived invariant property. So some counterexamples. So probably the most well-known, maybe equally most well-known example of a Noetherian a right Noetherian ring that is not left Noetherian is a 2 by 2 upper triangular matrix ring. So if we take R be this upper triangular matrix ring, so here I'm taking the ring homomorphism 5 from Q to R is just the inclusion map. Then this is right Noetherian. In fact, it's right Artinian. But its opposite ring is not. And because the rings on the diagonal here are commutative, the opposite ring is just the ring S that I've been talking about. So the opposite ring is not right Noetherian. And so it's also definitely not right Artinian. Okay, so this is a simple example that shows that the property of being right Noetherian or the property of being right Artinian are not derived invariant properties. So they are Morita invariant properties, but not derived invariant. Okay, and using some slightly more complicated examples, we can give examples to show that various other finiteness conditions are not derived invariant. So what about right coherence? Okay, so here's a way of constructing an upper triangular matrix ring, which is where R is right coherent, but the ring S is not. Again, this will be an example with commutative rings on the diagonal. So we want an example that is right coherent, but not left coherent. And one way of doing this is if we take lambda to be any valuation domain, its maximal ideal is not finitely generated, so a specific example of one of these is we can take if we take the usual usual valuation, sorry, on the p-adic integers, sorry, p-adic rationals, this extends uniquely to a valuation on the algebraic closure and the valuation ring is the set of elements in QP bar whose valuation is greater than or equal to 0. Sorry, is greater than 0. So this is the maximal ideal of the valuation ring. Then this is not finitely generated. So taking the ring of integers and the algebraic closure of the p-adix gives an example of a valuation domain of the kind I want, but any example will do for this construction. Okay, then if we take the upper triangular matrix ring, where we put lambda in the top left and the residue field in the right-hand column, then it's not hard to prove that this is right coherent. On the other hand, if we take the opposite, the corresponding ring S, which will be the opposite ring of R, then it's easy to see that this is not right coherent. And so this example shows that it's a property of right coherence. It's not derived invariant, so this answers Manuel's question. Okay, what about other finiteness conditions? So a lot of people who study non-commutative Noetherian rings are interested in rings that are two-sided Noetherian, are Noetherian on the right and on the left. Construction of cone, which has been used for sort of similar purposes before. So in 1977, Cone gave an example of an extension of skew fields, of non-commutative fields, which is finitely a finite extension on one side, but an infinite extension on the other side. So the dimension of L as a left K module is finite, but the dimension as a right K module is infinite. Okay, and so using the inclusion map from K to L as our phi, then if we take the upper triangular matrix ring KL0L, then this is Noetherian on both the left and the right. I think it's Artinian, in fact, on both the left and the right. Back to that, I think it is. But if we take S, okay, so this time, because these are skew fields, so K and L are not commutative, then S is not just the opposite ring of R. Of course, if it were the opposite ring, then because R is two-sided Noetherian, the opposite ring is two-sided. So, for example, here, we definitely need non-commutative rings on the diagonal. This is not, it's not Noetherian on either side. Okay, so being two-sided. Noetherian is not a derived invariant property. So one example I haven't been able yet to come up with an example for. So let me just finish with a question for you. What about being two-sided coherent? So any examples for that? I strongly suspect that it's not a derived invariant. Okay, so that's pretty much all I've got to say, except let me just repeat what I said at the beginning, which is that when I started looking at this, I thought some of these examples must have been known for ages, but I couldn't find any references. So if anyone can point out to me where any of these things previously appeared in the literature, then I would be very grateful to hear about it. Okay, well, thank you for paying attention. And as I say, it's been a pleasure to be back in this file.
So thank you very much for your very nice talk. Are there any questions or comments?
Can I start with a very naive question?
Yeah.
The property of being perfectness, a ring is perfect, right perfect, for instance, if every right flat is projective.
Okay.
It seems that it's obviously a Morita equivalent property, Morita invariant property, yes?
Yeah. So your question is it derived invariant? Oh.
Yes.
I don't know. Again, it's maybe I'll suddenly remember something in my thesis that answers that.
Great, thank you.
And there's a question in the chat.
Let me stop sharing. I can't see the chat.
I can read it for you. Why is the find theory you construct triangulated?
Okay, it clearly commutes with shifts, and you can easily check that it sends quasi-isomorphisms to quasi-isomorphisms, and that's enough to. I guess almost everything about it is fairly straightforward to check. You can check that it takes short exact sequences to short exact sequences, I think.
Oh, thank you. Any more question? And I have also a simple question. For the Morita invariance, there is a theorem which says that a property is Morita invariant if it is invariant on the corner and on the matrix. And if there exists such similar theorem for the derived invariant situation or not?
Well, not a very satisfying one. So for Morita equivalence, you need some condition on the corner. So I don't know what the term is, but yeah. So the problem is that for Morita equivalence, every Morita equivalent ring is just the endomorphism of a projective progenerator. And so that means that you can just take the direct sum of copies of the ring, the endomorphism of that, so the matrix ring, and then take a direct sum end of that. But for derived equivalence, the corresponding thing to look at is not progenerators, but tilting complexes, and they're the condition. Then it's not quite so easy to say how you get all tilting complexes.
Oh, thank you. Are there any more questions or comments? So let's thank the speaker again. Thank you very much for your very nice talk.